turn this one on if you want.
I'll get you to sit if you can, if there's seats. Hello everyone, and welcome to Toronto Metropolitan Formula Racing's 2026 Unveiling. My name is Davis McDonald. I will be your MC for today. I am a second year, going into my third year aerospace engineering student, and I am the composites manufacturing lead for Toronto Metropolitan Formula Racing. Today, we will be unveiling our car, is the main part, but we will also be giving a bit of an introduction to the design of our car and the process we go through, and also our competition that we are a part of, which is FSAE, the Society of Automotive Engineers. It is a competition that we'll touch on later. We're very excited for this year's car. We all put in a lot of work, including a lot of late nights, and yeah, it's going to be a good car. So before we begin, I'd like to acknowledge that Toronto is in the dish with one spoon territory. The dish with one spoon is a treaty between the Anishinaabe, Mississaugas, and the Haudenosaunee that bound them to share the territory and protect the land. Subsequent indigenous nations and peoples, Europeans and all newcomers have been invited into this treaty in the spirit of peace, friendship, and respect. Today's itinerary, you've already been a part of the arrival and welcome. We will now be having a presentation till about 3 o'clock, at the end we will unveil the car. We will then have lunch, and then you will be able to take photos with the car, check it out, talk to people, enjoy this car we've put a lot of work into. I would like to invite our team captain, Mose, to come and give an overview of our team and give a bit more information.
There we go. Hello, everyone. My name is Mose Ahmed. I am this year's team captain. I am a fourth year, now graduating mechanical engineering student here at TMU. A little bit about myself. I was in charge of the aero package for the last 3 years on the team. And this year I took on the role of team captain, where now I oversee basically every technical and non-technical part of the team, from managing, a lot of emails that you probably get from me, to also just the design choices that went on throughout the year. Before I get started into more about the actual car and the design specs, I want to talk about our team structure, how we kind of handle ourselves throughout the year. We have our system leads. Our team itself is broken down into 3 engineering teams and 1 business operations team. First, we have our aerodynamics team, which is handled by Ozge Adin, which is handling the aero package on the car. It's all the aero components, so the front wing, the rear wing, the under tray, so on and so forth. Make sure that the car stays stuck to the ground during dynamic events. We have Dejan Milodragovic, who handles the vehicle dynamics team, which you'll also hear from in a little bit, which handles basically anything mechanical on the team. Basically, from the chassis, suspension, tires, anything mechanical you see on the team is handled by Dejan. We also have our electrical powertrain team that handles basically anything that requires to get the wheel to move under its own power, the car to move under its own power. So that pertains things like our high voltage systems, that are like our battery pack, our motor, as well as our low voltage systems, which handle things like our data acquisition systems, our brake light systems, other safety systems that we have on the car, our vehicle control units, so on and so forth. And lastly but not least, we have our business operations team, which is handled by Andrew D'Onofrio. This is a very big part of the team, and a lot of you guys who are here from our great sponsors, you may have gotten a lot of emails from Andrew. He has basically handled a lot of the relationships that that we developed this year, a lot of the discussions we had, and so on and so forth. They also handle things like our media relations, our social media, as well as our recruitment, and a bunch more that Andrew will get into in a little bit. So a little bit about the team. I'm going to talk about who we are, what we do, give a bit of context to those of you who are not familiar. We are a team, a design team at TMU, which is led by engineering students. We're all students here on the team, at the university. And basically what we do every single year is we create and race an open wheel race car, an electric race car every single year. So that is from start to finish. We design, fabricate, manufacture, test, and race a new car every single year. It is an incredibly intensive process, which takes about 9 months to fulfill, which basically pertains from the week after we come back from competition, which is in June, to straight to the next year, into the June of the next year, where we go and compete. It is a 4 to 5 month cycle of design, then 4 to 5 months of manufacturing and testing before we go to competition. So it's a very, very heavy cycle. A lot of team members on this year, even just to get the car here at this unveiling today, for the last month, basically spent every single day and night in the shop, like 12, 14, 16-hour days in the shop, every single day, including weekends. So I'd like to give a big round of applause for everyone who did that. So what we also do is what we specifically do is we compete in a competition called Formula SAE. It is governed by the Society of Automotive Engineers. It is handled by, it is an international competition. So there are competitions in Germany, Switzerland, all across Europe. The biggest competition in North America is FSA Electric Michigan, which I'll get a little bit more into detail in a bit. We also do a lot of things with conducting educational and charitable activities. So we do things like AWIM, which is A World in Motion, where we go to elementary schools and we teach young students about STEM to inspire them to take on STEM education in the future. So we do that every single year. We also attended the Women in Engineering Conference this year, which also is a big thing that we try to make sure that we are making the space a welcome space for women in engineering, as well as women in STEM in general. We also go to the Eng Expo twice a year, so in the beginning of the year and the end of the year, as well as our Frosh in the beginning of the year. Whenever we have our new incoming engineering students, we kind of teach them about STEM, teach them about what we do on the team, and just overall kind of inspire people to kind of get ready for engineering and show them how cool it can be and beyond just the classroom. We are a very diverse team and a very large team. So at the beginning of the year, we had just about 50 team members around leads and apprentices included. It's a little bit more than that now, but if we include even people that just helped out throughout the year to manufacture, mentees, and so on and so forth, it is a little over 100 to 150 almost, I would say. It's a very diverse team. So we're not just engineers. As I mentioned, we also have a business team as well. So we have people representing our team from commerce, arts programs, and very different all across the engineering as well. So we have aerospace, biomedical, electrical, mechanical, so on and so forth. So a little bit about the competition itself. It's split up into two different categories. We have our static events and our dynamic events. The static events are split up into three specific events. We have the business event, we have the cost event, and the design event. The business event handles basically a case scenario that is provided by SAE, which we are then to prepare and present to them. And there's multiple rounds. There's a preliminary round that we do online. Then there's a second round that we do online. Then if you pass that second round, you go to the in-person rounds in person at competition. Then there's a finalist round with the top 10 at competition for a business presentation itself. Then there's cost scenario, which essentially is another aspect of the competition itself, which every single part on the car has to be inputted into a cost database, essentially. And it kind of puts us as a leveling of the playing field for there are a lot of teams that maybe have higher budgets or lower budgets. It levels the playing field a little bit. And we are to input that, and they check for things like our accuracy of our cost report system and how we implemented it and so on and so forth. Then the most important one to us is the design presentation with static event. The design presentation handles the actual it's almost like a defense of our design. So it's split up into different categories. We have chassis, driver interface, data acquisition, powertrain, aerodynamics, and so basically when you go there, there are judges from the industry who you are presenting the design to, and they will basically judge your design back to you and give you feedback and give you a score overall. And it is one of the highest scoring events at the competition in of itself. It ensures that we're not just building a race car, but we understand what we're doing and we're actually applying the things we learn in our classroom and putting it on in a physical car and understand the theory behind it as well. So that's the emphasis behind that. Then we split up into the dynamic events. The dynamic events are acceleration, skid pad, autocross, and endurance. Acceleration, you can probably imagine, it's basically like a drag race, but for one car, and basically it measures the car's straight line acceleration capability. Skid pad is a figure eight, which measures the car's cornering ability. We have autocross, which is a single lap performance evaluation of the car. So it's a single lap that the car drives around, and they get to do it 4 times with 2 different drivers. And then we have endurance, which is the most points that can be scored at a competition. It is a 22-kilometer endurance sprint, which essentially is on track with different cars at the same time, but you're racing the clock. And it is also scored simultaneously with a sub-event called efficiency, which also measures your overall efficiency of your battery pack by the end of the event itself. A little bit about our goals and how we went into the season this year. So a big part of our design and our overall implementations of this year for how we went into the season, first and foremost, we went in with a points-driven design goal. In the past, we had more kind of soft goals that were targeted to kind of ensure the overall vehicle running and such, so on and so forth. But this year, we had performance at the forefront of our priority. So it was driven by a points-driven target, which we did through simulations for things like a power versus mass versus points plots, and a few other trade-off studies that we did, which, for example, we were able to get a goal of our acceleration target to be 70 points, which dictates about a 5.4 acceleration time for our acceleration event. We also worked on improving our overall system integration across the whole team. So we wanted to make sure that we are, with these simulations that we did, we're integrating them within our systems and within each other's systems as well. So everything is all one package together and everything is supposed to work together rather than on its own. So developing these vehicle simulations, we were able to get things like our design targets, such as an overall weight target. Our overall weight target this year was 205 kilograms. I'll get into where we're at this year, but that was dictated by the simulations that we had earlier, and from there we were able to trickle that down and split it up into different budgets for weight budgets for the system. So electric powertrain got so and so kilograms, aero got such, and VD got such. So from there, then those weight targets were then trickled down into their subsystem. So the steering system got so much, suspension got so much, and so on and so forth. So it's making sure that everyone is working towards a simultaneous goal, which is driven by performance at the end of the day, to make sure that we have a competitive car on track. Finally, we also did a lot of revitalization of our hiring process, as well as how we overall train our team members. So what we did was we in the past, we used to have a process where you could kind of just come into the shop, join the team, work a lot with team members, and eventually in a year or a year and a half, you could probably become a lead or an apprentice on the team. It worked. However, one problem that we found was that there was a low member retention because some people want to see progress faster, but also we saw that it took too long, and a lot of us are here for 4 years, 5 years to graduate, so we don't have a lot of time to train people, get them really ready for a competition, and build a car. So what we did was we fully relooked at how we do that, and we implemented a new recruitment process where we hire team members specifically on every semester. Andrew will be able to go a little bit more into detail about that. From there, this allowed us to then have onboard new team members every single semester. And this also allows the team members to then go from one semester as a new member that knows nothing about the car to being able to design components on the car within the next semester. So a big improvement in overall the ability of each member that's brought onto the team to be able to actually take on design tasks, and overall in the future foresee themselves becoming a subsystem lead pretty quickly and being able to take on more responsibility and roles as they move on forwards. Just some quick looks about the vehicle architecture. Our wheelbase is 2.8 meters, our track width is 1.7 meters, and our height is 1.2 meters. We are still running a single motor rear wheel drive motor, which is an MRAX 228, which is mounted at the rear of the car. This year we have also, we are again implementing a full aerodynamics package. However, we have implemented a new component called the undertray, which you will get to see, and Ozier will cover that in a bit. We've also made some significant advancements, such as implementing an active aero system. So Ozier will also talk about a lot of the implementations we made on the aero system, and which you'll kind of get to see in a little bit. Some key design improvements that we had this year. So last year, our car weighed 230 kilograms, which is a little above the average weight of the cars at competition. So they're around 225, 220 kilograms. So we were a little overweight last year. This year, we were able to bring down our car to 210 kilograms. So from 230 to 210, so a 20 kilogram reduction in weight, which is a lot. We are now in a significantly more competitive category as to where our car actually sits with the implementation of a lot of new components on the car that weren't there last year. We also were able to up our battery pack voltage, which gives us more power at the wheels from 378 volts last year to this year's car being at 440 volts. And we also doubled or nearly doubled our downforce on the wings, on the whole overall aero package as well, which makes sure our car is more stuck together. And this was driven by an overall system integration with suspension. And they asked us for a system target for how much downforce they want to have on our car. And we were able to provide 820 newtons at 80 kilometers an hour. Yeah, and I'll hand it off to Davis.
Thank you, Mose. That was very interesting, insightful. We'll now have Dayon coming up to give a bit of a deeper dive into vehicle dynamics.
Just clip it onto your like this. You need that.
And then this.
Does this mic work too?
Yeah, both work.
Okay. All right. Hello, everyone. My name is Dejan Milidragovic. I am currently finishing, or I just finished my 4th year of mechanical engineering here at TMU. A little background of myself on the team. I joined this team when we first transitioned to electric over in 2021, 2022. And since then, I've been heavily involved with the vehicle dynamic systems. I've designed numerous components on the car where eventually throughout my tenure on the team, I've become the vehicle dynamic system lead as well as the primary designer for the chassis and the outboards on the vehicle itself. So a little bit of an overview of what vehicle dynamics does on the team itself. We are primarily involved, like Mose mentioned, with the mechanical design of majority of the components in the vehicle, mainly with the systems that pertain to controlling the behavior of the car when it's on track, as well as the components that the driver interacts with to make sure that the driver is able to control the vehicle properly, safely, and obviously comfortably. Vehicle dynamics is currently split into a total of 8 subsystems, which include the frame subcomponents, driver interface, drivetrain, suspension, outboards, brakes, steering, and tires. And a bit of an overview of the system itself is at a system level perspective. What I did with the system this year was take a huge emphasis in terms of building a solid foundation of how we model our vehicle in terms of tying our subsystem goals to quantifiable parameters that are equivalent to to the frame, as well as the packaging with other components that are found in the system in that region. Another advancement that we made in the suspension, steering, and upright systems themselves was the change in designs of what we're, for some of our components. What that looked like was we've transitioned from using welded and casted aluminum materials for our suspension bell cranks and our uprights, which are seen here, to CNC machined aluminum parts, which allowed us to have more confidence in the strength of our designs. We were able to maintain a high level of stiffness in these components while also maintaining a low weight that we were obviously aiming for in our vehicle goals. And a product of that was also reducing overall our vehicle compliance in the suspension system itself, thereby enhancing our chassis stiffness and reaching those goals that we have set out in the chassis itself. Moving on to driver interface, one of our most important systems on the car. Driver interface is totally centered around all the components and all the parts of the car that the driver interacts with directly. Some of those components include the pedal box, the seat, and the steering wheel. And the basis of the driver interface system is built upon our ergonomic testing that we do in shop. You can see in this photo here that we have this ergonomic testing rig, which is something that we've built in shop 2 summers ago, which essentially tests each of the drivers' optimal control placements in the vehicle. And what we do is we cascade those results into the design of the chassis, into the design of the specific components, such as the pedal box itself, to make sure that all of our drivers are able to comfortably drive the car. As a driver that is comfortable is able to push the car more, and pushing the car more obviously gives us faster times on track. So what that came out from the ergonomic testing was that cascaded into the brake and throttle pedal adjustment, where now we have up to 6 inches of pedal adjustment, allowing us to comfortably accommodate all of our drivers that are in our vehicle. Some other highlights of the driver interface system include the custom carbon fiber bucket seat that we create. And a huge change that we made this year was implementing custom foam inserts that are molded to each of our drivers, so that whenever a driver gets swapped out of the car, we're able to place in a custom foam insert so that they have the most comfortable, most optimal seat positioning in the vehicle. Again, having that confidence in the car also comes with a lot of, also has a lot to do with the comfort that they have in the cockpit itself. Finally, moving over to the drivetrain system itself, we've made major advancements in the drivetrain system this year. For those of you that don't know, the drivetrain system is mainly responsible for the packaging of the motor and the differential of our car, and as well as the selection and design of the components that are responsible for transmitting that torque that's produced from a motor to our rear wheels. So what that looked like this year was actually implementing a single motor differential mount design, which enables us to package the differential and the motor much more tightly than we have in the past. You could see here on the photo above that this was our previous car in TM25, where we would run the motor on top of the chassis with the differential under it. And we've transitioned to with that hybrid mount design, we're able to drop that motor down into the chassis, which allows us to free up a lot of that space that's above the chassis, which gave us a lot more freedom to design our suspension the way we wanted to. Specifically pertaining to the load paths that we're seeing from the wheel to the shock, or to the bell crank from the shock. We've dealt with a lot of excessive deflection and failure in the parts there with suspension last year because of how much in the way the motor was in the previous years. So dropping that motor down significantly improved the integration that we have across the whole car, especially in the rear, which enabled us to design our suspension with a lot more confidence and without any sort of concern in terms of parts failing like we have in the past. This is our team here. So we have Omar Ishmael, which was our suspension lead. He was in charge of majority of the suspension design and all of the kinematics and vehicle dynamics modeling that we've done in the past. Marta Senkiv was our tires lead. Luca Flame was our manufacturing lead and also our steering lead. Andrei Jaskovic was our drivetrain lead. Filip was our driver interface lead. Andras was part of steering as well. Ethan was our brakes lead. Philip was our frame apprentice. Benjamin was our suspension apprentice as well. Drew worked out with the frame subcomponents. Mateo as well. Ronnie was our drivetrain lead. Reese was also on drivetrain. Jonathan's a new apprentice that we've had for frame, which has been a huge help. James as well for driver interface. And then below are our mentees that have been recently enrolled onto the vehicle dynamics system as well. I'll pass it on to you, Davis.
Thank you, Dayon, for giving us all a lot more understanding of vehicle dynamics. We will now be hearing from Özge, and she's going to be speaking on our aerodynamics system.
Huge difference in angle, just like our JRS. Hello everyone, my name is Özge Eden. I am the head of aerodynamics for our TM26 car. This year is my third year and final year on the team because I'm graduating. This year also marks our third year for our aerodynamic systems. Hopefully this is going to be the only beginning of many more years with aero development for TMFR. Aerodynamic system is the main system responsible for generating the negative lift, also known as downforce. This helps the car significantly, especially during cornering, by increasing the tire grip and overall stability of the car. Our aerodynamic system consists of 10 subsystems. Those are front wing, rear wing aerostructures, bodywork, which includes the nose cone, side panels, and the rear cover. It is also a new component this year as well. And the undertray, our brand new subsystem, and the CFD machine can solving, as well as the accumulator cooling systems. This year, we made major advancements across the system, especially because it is the first year we fully integrated the undertray and rear cover into the aero package. So starting with the front wing, this year we improved the design by adding vortex generators and curved end plates. This helped control the airflow being sent toward the rear of the car. We also added another lofted section on our main element of the front wing. We positioned it closer to the ground. And the reason was that after running a lot of CFD cases, we wanted to open up an air channel for the undertray unit. Structurally, our front wing is also more stable and less deformable compared to our last year's car. We rigorously designed it by bonding aluminum end strips and using carbon fiber sandwich panels on our lofted sections. We also redesigned the mid plates because last year we had two mid plates that we thought that it could help more for the stability of the wing, but it turned out that having the gap there help us lead more air towards the undertray section, and it is more stronger than last year's design. You will see it in a few minutes, hopefully. So moving to the rear wing, our design includes additional components this year. Those generate more downforce, such as gurney flap on the third element and the winglets. We also kept the slit design the same. Those help cancel the vortices from the inner and outer side of the end plates. But more importantly, this year we integrated an active air system, which is also known as drag reduction system, DRS. According to our CFD results, the DRS is when the DRS is activated at 80 kilometers per hour, it reduces the drag generated by the overall car by 36%, which is huge. Yeah, that covers the front wing and rear wing under tray. As mentioned earlier, under tray is our biggest downforce generator, one of our newest components on the car. With the addition of under tray, the downforce generated by the car has doubled this year, and compared to our last year's car. And obviously the manufacturing was never easy, but we had an amazing team who worked extremely hard to make it happen. The under tray consists of an underbody section, as you can see here, that covers the underside of the car and connects to the Venturi tunnels. We went through more than 10 design iterations and selected the final design based on CFD results from multiple cases. The design also includes 3 strakes at each inlet region to guide the airflow into the tunnel. It also includes vortex generators on these sides. And the vortex generators obviously will help to seal airflow underneath the car. We also do have tire walls here on each side, and they are to reduce the dirty air generated near the tires. So structurally, we have mounted 8 mounting points drilled into the floor, and we also have 4 support tubes to provide structural stiffness. So on this slide, you can see the comparison of our TM25 car versus our TM26 car. All these are from our CFD setup. Both ran at 80 kilometers per hour. Our TM26 car shows a major improvement in aero performance, and the lift coefficient, as you can see, rise from 1.6 to 2.76. And the total downforce increased from 445 newtons to 821 newtons, which is almost doubled. This improvement mainly comes from the updated aero package, including the under tray rear cover, optimized wings, and better overall aerodynamic performance. You'll also see that there's an increment in the drag from 326 to 367, and which was expected, obviously, because the car is producing significantly more downforce. So lastly, you can also see that our aero balance is also shifted from 52% front heavy to 44.6% front, which gives the TM26 a more rear supported and balanced aero package. And as mentioned earlier, our bodywork includes side panels, nose cone, and the rear cover. On the slides, you can compare the TM26 nose cone design with our last year's nose cone design. This year, we designed a more curved lower section, which allows the air to flow more cleanly alongside of the car. And by keeping the flow attached and reducing areas of slower air, the design helps reduce stagnation effects. And here we also have our rear cover design. And we have the rear cover for two main purposes. The first one is to help us to pass the rain test by acting as a waterproof cover for our electrical components at the rear end of the car. And the second one is to help reduce the dirty air at the back of the car. And For the side panels, for the rear cover, we also incorporated a copper mesh to help with grounding and to reduce the induced charging from the high voltage components. This is important because carbon fiber is naturally conductive, so we needed to consider both aerodynamic and electrical safety requirements for the design. Overall, our TM26 car represents a major step forward for our aerodynamics system. We didn't only optimize the front wing and rear wings, but also introduced a new components, such as undertray and the rear cover. Those improve the structural reliability and we also integrated the active aero. These changes helped us significantly improve the car's downforce and the drag performance and overall aerodynamic efficiency. Last but not least, here are our amazing members behind the TM26 aero package. We have many more who we couldn't add to the slide. There are indeed the wings behind our wings and all of our other aerodynamic components. These members supported every part of the design, from the front wing to rear wing to undertray bodywork, CFD analysis, and their structural work. Every component on the car represents their effort, problem solving, and commitment throughout the year. Thank you.
Thank you, Özge, for telling us all about Aero, which is personally my favorite, but I'm a bit biased. Next, we will have Oais telling us about our electric powertrain system.
Hello, everyone. My name is Oais Patel, and I am this year's low voltage lead. Me and Emiliano, who is the high voltage and electric powertrain lead, worked on this alongside our team together. I am a fourth-year computer engineering student. I'm currently doing my co-op, and yeah, we'll start talking about the high voltage and low voltage systems on this year's car. I hope you guys are still interested, because I don't know, maybe you guys are like half an engineer by now, listening to all the details. But let's get into it. So starting off with the high voltage, our car is electric, so obviously there's going to be very high voltage that will need to power this car. Like you guys know, there's many electric cars out there, Teslas, and many other EVs nowadays. So this is the main heart, or you can say the thing that powers the car. So we have a high voltage system, as you can see on the screen over here. We have a new 440 volt battery pack this year, like Mo said, an improvement from last year, approximately like 60 something volts. As you can see, we'll do a comparison later with the side-by-side CAD design overview. You can see that the battery pack is completely redesigned and the packaging is completely different as well. So what's inside the battery pack, right? We have AA batteries that we usually use in like remotes and TVs and stuff. As you can see on the screen right here, it's the same thing or something similar. It's the 21700 cells, which are made into modules, and then there's multiple modules that are put into the battery pack. They are focused on packaging strength because you also have to take into consideration that this car moves very fast, and if there were anything like any incidents to happen, this battery pack has to stay intact. So you can see over here the design. It has the battery cells itself. It has the CNC'd composite FR4 structure, which is right here. And then you have the laser cut 0.15 millimeter laser cut nickel bus bars. So what this does is just connects all these cells together, and it provides efficient power transfer. Moving on, continuing on the battery pack design, which is the overall structure that holds these cells, we can see that it's made out of metal or aluminum. And this also plays a significant part in the weight goal that we want to achieve, right? So we need to focus on this, optimizing this as well, because it obviously transfers heat and carries a lot of weight. So this year, we ran many simulations using MATLAB for battery module representation, simulating power draw, heat, and all of these elements as well. As you can see over here, here's a little module, and here is our battery pack. So this is the container. As you can see, it's made out of 6061 aluminum wall panels. And this year we used a new wall joining method for reduced weight and size to achieve our overall team goals. So as you can see right here, for the high voltage comparison, you can see last year's system where we had a 60 kilogram battery pack. It had a volume of 62 liters, and the container weighed 13.7 kilograms. And now you can see for this year, we have a 45 kilogram battery pack, which is a 25% reduction, which is quite a lot. And there's also a 27% reduction in the overall container volume. And this, the container itself is also 45% lighter. So this is a significant portion that played, obviously, in reducing the overall weight for the car. Now low voltage, this is what me and my team worked on, or our team worked on. This is kind of like, as you can see, the design, it looks like the nervous system, and it basically is the nervous system of the car. So it basically powers, so we have all of these components together. We have the active aero, we have the pedals, we have the battery pack, but what connects all of this together and actually listens to what the driver is inputting is the low voltage system. So this takes in all the sensors, reads in all the sensors, captures what the car is doing in real time, and outputs, tells the battery pack what to do, tells the car what to do, and this can turn every session of running into a training session, and we can get lots of feedback from this as well. So as you can see, there are a few boards on the screen. Some of these boards are DC to DC converters, which convert. So we have a 30-volt battery pack. As you can see, the first bullet point over there. And in the diagram, you can see as well, right over here, this is our low voltage battery pack. We have designed it this year ourselves. And this is 30 volts. And many of the components on the car need lower voltage. So we have DC to DC converters. We have a low voltage battery management board. We have the wiring harness, obviously, like we've seen in the last picture. We have the data logger, and we have a sensor suite that we also designed this year, which is a very major component as well, along with the telemetry and the dashboard. So here's a little video. I don't know if you guys can see very clearly, but this is a telemetry dashboard that we designed this year. In previous years, what we had to do is we had to pull the SD card out of the car and manually graph it using Excel. Now, if you think of that, you have to go back into the shop and you have to wait for the testing session to end, because taking it out of the enclosure and removing all of these elements obviously takes a lot of time. So this year, what we have is we can directly plug our laptop or anything in, and we're moving on to fully wireless as well. But we can just plug it in, and once you upload the data file, or if you import it from the car's TNC or the data logger, we can view it right away. And in the video, you've probably seen the plots as well. So this is a major milestone. This can help us achieve, we can view acceleration inputs from the driver, see how the driver is responding to the acceleration, see how the steering angles respond to the driver, how much, is there oversteer, is there understeer, is the battery temperatures too high, you know, all sorts of things. Do we need to change the maximum current of the pack? All of these things now can be done during the testing session itself, which would save us a lot of time and, most importantly, gather lots of data. So now we can see a little comparison from the previous year and this year. Last year we used off-the-shelf low-voltage batteries, and we had uncertain runtime because obviously we didn't design this ourselves. We don't fully know obviously there's a data sheet, but we have more insight of when we design our own, and we can design it to our needs. So this is one of the major things we designed. We had sensors last year that we were thinking of installing, but we didn't really get to install them, but like linear potentiometers for the suspension travel. This obviously can provide lots of important data as well for the suspension, the stiffness of it. So this is also a few things that we've improved this year. And this year, we've also changed our driver inputs that go to the motor controller to digital. Now, there are analog signals and digital signals, so obviously digital is more reliable, and the pedals can also have a pedal map because when you drive the car, it's not always linear. This is better for the driver specifically, and it can be adjusted for each driver as well. So this is one of the main things as well. Like I said, we also had the plug-in cable that we can do for the data analysis instantly. So we can do multiple tunings per session. And last but not least, we can make decisions during the track testing time and not after during multiple sessions. And obviously, all of this, there's lots of work, could not be done without our amazing team that we had. Lots of members that spent many hours designing and also manufacturing. Obviously, doing something from scratch takes a lot of effort and time. So shout out to everyone on the team and anyone that's also missed as well. Great job, and thank you. Hope you guys learned something new for the high voltage and low voltage system.
Thank you, Awais, for telling us all about electric powertrain, something I still cannot wrap my head around. It's been a year and I'm nowhere near closer to understanding it. Next, we'll hear from our business operations lead, Andrew, and let him take it away. Thank you.
Another goal of ours was to place highly in the business presentation at the Formula SAE competition. The business presentation counts for 75 total points towards static events. So it's absolutely imperative that we're trying to get as many points as possible. And the third goal that we had was to kind of reignite our social media. Social media is our #1 platform for exposure. It not only ensures that our team is getting the recognition that they deserve, but also our sponsors. Our sponsors are quite literally the lifeblood of our team. We would not be able to do what we do without our sponsors. So by kind of reigniting our social media, we can ensure that they're getting the exposure that they deserve. So I'll get into some key highlights from the season. So I'll first talk about our recruitment. So through our redesign of the recruitment process, we first established 6 orientation nights in total. So these took place in the fall and winter semester, so there's 3 nights per hiring season. So these hiring seasons were kind of the precursor to our recruitment applications that opened shortly after each orientation night. So we held 6 orientations in total across this year, and we saw over 550 attendees at these events, and many of so applied to our team, some of which are also on our team now. So through this recruitment, we onboarded 58 mentees throughout the entire season, and many of those have been promoted since then. So I'll talk a bit about the mentorship program and the whole redesign. So how it used to be was, it would take a lot, like Moses was saying, it would take a lot of time for people to get promoted from one role to another. So a lot of people would stick around as general members without clear role assignment for a long time. So we wanted to change that, make sure people were getting on a proper pipeline, getting promoted faster, learning kind of their focused subsystem quicker and more effectively. So how we did it was we set up our recruitment applications. We hired 58 mentees, like I said. These mentees were assigned roles towards a particular subsystem, and after these roles, they were promoted after 4 months. And this is part of kind of a rotational program, so every 4 months, new mentees are onboarded, and those mentees are subsequently promoted. So this not only ensures that people are getting promoted faster, they learn their subsystem earlier, they stick to one, they're not kind of getting their hands full with a lot of different ones, and it makes for kind of a brighter future for our team. So a highlight we had for this year was out of our fall applicants and hires, we promoted 19 mentees into apprentices. So if you take a look around, a lot of the members on this team were not here just 8 months ago. So it's a great feat for our team. It's part of a big goal of ours to kind of build a brighter path and ensure that our team has success for seasons to come and even decades to come. We also attended various events to kind of wave the flag, bring some exposure towards our team and our sponsors as well. So 2 of our highlighted events this year was the Women in Technology Management Empower Tech Conference. This event saw over 100 attendees, so we got a chance to kind of tell a lot of like-minded individuals what we do. This was also great for recruitment. We got a few applicants at this event and at the Honda Indy, which we attended in July as well last year. On top of this, we have some great news about competition. So for the business presentation, which I'll tell you guys a little bit more about, the FCA presents each team with a case, with a business-related problem. For example, this year was a sponsorship pitch that we needed to pitch to a series of judges who are also industry professionals. So back in December, we presented it was a written component of the presentation, and I'm happy to say we advanced to round 2 amongst only 49 teams out of 120 teams. So this kind of paves the way for us to make it into round 3, which is only 10 teams out of the entire 120. And by making it into the finals, we guarantee a great amount of points that can contribute towards high placement at the Formula SAE. And I'll get into a bit of our team. So as you can see on screen, we got a pretty big business team, and a lot of these members are new as well, but they've been learning quick. They've been getting their hands full of work and really making our team and giving us the success we've had this year. We have Anisha, she's our events lead. She put together this great event. We have Awais, he's our social media and sponsorship lead. Abdullah, he's our sponsorship apprentice. Mishma, she's our events apprentice. Eric, he's our graphics apprentice. Ryan, he's our media apprentice. Laraib, she's our events mentee. Philip, he's the business presentation co-lead who co-led it with me. Justin, he's our one of our livery leads, and Eliza, who's our photography apprentice. So after this, I just want to switch slide, give a thank you to all of our sponsors. Like I said, without these sponsors you see on screen, we quite literally would not be able to do what we do. We thrive based off their support. And as you can see, these sponsors are of varying levels, but I also wanted to give a thank you to the 2 companies that sponsored our event. As I said, lunch is on its way, which will be from Poulet Rouge, who was kind enough to sponsor this event, and Compass Coffee, who provided our chai that you can see at the entrance. And I'll let David back up so he can give a nice conclusion.
Thank you, Andrew. That concludes the information part of the unveiling. We now can get to the much more exciting part of the unveiling, which is our TM26 car.
Yeah, so that wraps it up. Thank you so much, everyone, for coming out today. Again, lunch is on its way. You're more than welcome to come take a look at the car. You can come take a seat in the car. You can take pictures. You can ask us a lot of questions if you'd like. As soon as I have more information as when lunch is available, I will let you all know. But in the meantime, you're more than welcome to come out and take a look at the car.
Just be careful, Mike.
Oh. Also, just a quick disclaimer. Please be careful around the front wing and the under tray. There are no step stickers, but try not to step on them. They're not meant for human weight. so please don't step on the components that you see, but you're more than welcome to take a seat in the car and take pictures with it.
The speaker shut off.
I realized, yeah. That's all right.
It's fine.
Yeah.
So I started playing. I was like, why is it so quiet? The phone's on full volume.
Yeah.
That's fine. I gotta dip out. I gotta get to work.
Huh?
I gotta dip out. I gotta get to work.
No problem, man. Appreciate your help. Easy, man.
Good job on the position. That was a really nice touch.
I think so?
Yeah. My opinion was a little bit off, but it's still good to just show and explain it.
Yeah, there was definitely, I started to feel it, like I was like, okay. But it kind of was necessary because lunch is a bit late.
That's good. Nice, yeah. It was a really good touch. I would
Active arrow.